The next two questions pertain to the situation described below. Ball's motion is represented by the velocity time graph. Okay, velocity means that there is magnitude and direction, and time graph. Okay? Okay, so let's see. Velocity, time. Which of the velocity time graphs above best represents this statement? An object has zero acceleration at t equals 2. So zero acceleration. So dv dt. So acceleration equals the first derivative with respect to time. And we say that equals 0. Therefore, we're looking for a max or min of this graph at time t equals 0. Or time t equals 2. So we got this one, possibility. This one, possibility. No. 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 Alright, so we're between A and B. And we're also told that t equals 2.5. It is moving in the positive direction. So moving in the positive direction means it has a positive speed. And since we're looking at a velocity time graph, it means it has to be positive and slowing down. So 2.5 right here, negative speed, so it's not A, so we know it's going to have to be B. 2.5, positive, and slowing down means a negative acceleration, which means dv dt, derivative of velocity with respect to time, is going to be negative, which means a negative slope, which seems true because it's going downward. So the answer here is going to be B. Who would do this? Who would do this? Look at this, look at this, look at this. Right here. So it goes B associated with A associated with B, and then like C, D, E, they're like, yeah, okay, those are normal. Okay. So the answer is graph B, which in this case is answer A. Okay. Which of the velocity time graphs, okay, represents this statement? The object is moving in the positive direction. I probably should erase all my marks. There we go. Delete. Click. The object is moving in the positive direction and speeding up at t equals, positive direction. So that means moving in the positive direction, which means it's positive, and speeding up at t equals 1.75. So 1.75 is about here, so it's possible. So no, because it's negative. 1.75, also possible. Nah. So object is moving in a positive direction and speeding up. At 1.75, the object has negative acceleration at 2.5. 2.5, negative acceleration. Yep, because it's downward slope. 2.5, no, 2.5. Okay, so the object is moving in the positive direction and speeding up at 1.75. So this is positive because positive direction, moving in the positive direction, and speeding up means upward slope. Okay, so I'm going to look at these again just to make sure I didn't miss something. Click. Purple. So at 1.75, which is right here, right there, right there, right there, right there, and right. Oh, that's confusing. Right there. So it needs to be positive. So that's negative. That's positive. That's negative. That's positive. So okay, so our candidates are B and D. And speeding up. So B, it still has a positive slope at 1.75, though it's small, so this one's possible. Okay? The object has negative acceleration, so the only one that's left is B, so we know it's going to be B. The object has negative acceleration at 2.5. 2.5, negative acceleration. The derivative of the velocity graph is the acceleration graph with respect to time. So it's going to be a downward slope at 2.5, which is true. This has a downward slope at 2.5, so that just confirms that the answer is graph number B, which is answer number C. I know that those are letters, not numbers, but this is so silly anyway. They should just match up the A's with the A's. Make life simpler. I don't even feel bad. Okay, next problem. The box of mass 1 is 10 kilograms. So I'm going to do 10 kilograms is on a frictionless surface. I think those hashed line marks mean that the surface, the bottom, the ground, doesn't move. So it doesn't mean friction or frictionless. It means doesn't move. A small box of mass M2, 3 kilograms. Nope, didn't look quite right. There we go, 3 kilograms. Is placed on top of the larger box. A system of boxes is initially at rest. A horizontal force, initially at rest, that's good. Good to know. A horizontal force F is applied to the lower box, pulling it to the left as shown in the figure. Okay? The coefficients of static and co-friction between the boxes are these. So K is for kinetic, S is for static. And it makes sense that the static coefficient of friction is larger than the kinetic. That's just the way it normally works. There is a physical basis for why that's usually true, but I will not go into that. So initially the two boxes are reserved to move together. Check. The small box remains on top of the large box. Okay? What is the direction of the friction force applied by the smaller box M2 on okay. So the idea here is this box is being pulled this way, which means this box, if your camera is keeping pace with the smaller box on the bottom, then it would appear as if this top box is going to be moving to the right. So the motion of M2 relative to M1 will be to the right. And friction, by definition, opposes the direction of motion. So you're going to have force friction going to the left so as to oppose the relative motion between M2 and M1. Think of it this way. You pull M1, M2 is naturally going to want to slide off the back of M1. And so the friction force is going to actually be in the same direction as F, so to oppose that from happening. So what is the direction of the friction force applied by the smaller box M2 on the larger box M1? So it will be to the left. What is the maximum force that can be applied before the small box begins to slide relative to the large box? Okay, so we're going to do so we want to find out how fast can we pull that, how hard can we pull on the bottom box before the top box slides off. So we want to find, let's see here, force, nope, not going to do it that way. Yep, force, friction, small box, call this 2, it's on M2, will be the normal force times mu, and this will be mass times gravity, this is mass 2, times gravity, times so they're not sliding yet. So before it begins to slide, which means it's not sliding, which means we're going to use mu static. So we're going to have, I think it's 3 kilograms. So we have 3 times 9.8, I'll do 9.81, just to be a little bit more exact, times 0.29. And this will give us the mass times the acceleration. And this will give us the maximum acceleration that we can have before the box starts slipping. This will be the force friction, the maximum force friction. And then here I just canceled the 3 here because what I want to do is I want to find the maximum acceleration, not necessarily the maximum force. And so force equals mass times acceleration. This is M2. That 3 is M2. I should have just left it as M2. I didn't. Long story short, the maximum acceleration we're going to be able to have is 9.81 times 0.29, which is going to be about 3 meters per second. On clear, 9.81 times 0.29. There we go. 2.8 2.8449. Okay, so now that's the maximum we can accelerate the box system. Well, okay, that's the maximum we can accelerate box number 2. But since they're connected and they're not sliding, at least not yet, the idea is that's the maximum we can accelerate both boxes together. So force, this is the big F that we talked about, equals mass times acceleration. And in this case, we're going to do mass total times acceleration. Acceleration total is assumed. So the mass total, because we're accelerating both boxes, will be 13 kilograms. So this will be 13 times 2.8449, which equals, I don't know, 42? No, maybe. Times 13, 36.9. And this will be newtons. So one of the things you want to be careful for, let's go with this one, call it 37, is you want to make sure you're using the 13 and not 10. Because if you were using 10, just the acceleration of the, because you're not accelerating just the bottom box, which would be intuitive to think that, okay, we're accelerating mass 1 here. Well, you're accelerating mass 1, but you're also accelerating mass 2 by that force of friction joining them together. So an easy answer to get here would be 10 times 2.8, which would be 28, which you can see is a possible answer here. That's a good false answer, a human performance trap there. So that's why you want to use 37. You want to use 13 kilograms and not 10 kilograms because you're accelerating both of them together. If the boxes start from rest and a force of 12 newtons is applied until the boxes moved a distance of 2.5 meters, what is the work done by friction on the top box, M2? You may assume that the boxes move together. Okay. So this is actually this is a conceptual question, but it's fairly complicated. So what's saying here is we're pulling this box this direction due to the force F, and it's asking for work done. So whenever you see, okay, what is work done, your first thought is work equals integral F dot dr. If you're familiar with calculus, these are both vectors, and that's a dot product between the vectors. And then usually you'll see this is F times d, which is also think of as mass times acceleration times distance. One of the mnemonics that you can use to remember this is work makes me mad. It doesn't. I enjoy work. It gives me purpose and meaning in life. But as your mnemonic, you think, all right, work equals mass times acceleration times distance. And this, so what we have here is we're like, all right, we're given a force, we're given a distance, and we can use this force to turn it into, and we can use a force of friction up here if we want, which is 0.29 times the normal force, mass times gravity. And you can kind of think that, all right, so we have a motion and we have a force, therefore we have work done. And that's not actually true. So we have work done by F to get the whole block system accelerating and moving. But there's no work done by friction. This is asking, what is the work done by the friction? So this equation right here, which is kind of the basis of what we're talking about, work equals integral F dot dr, that doesn't really encompass the whole story because you need to know, or you need to understand or believe, if you will, that what matters here is that the force the change in position has to be due to the force that's being applied. If there is a force being applied and in some completely different unrelated circumstances also motion, that doesn't matter. That's not what gives you this work here. So since the relative motion, the force friction, which is right here, force friction, scooch up so you can actually see what I'm doing. Force friction right there, that's not providing you with any work being done because there's no relative motion between 1 and 2. This force friction is not resulting in relative motion. The motion is all due to this force F right here. So since there's no motion due to the force of friction, then this F dot dr is meaningless. The relative motion that we're talking about here, this displacement, this r, this dr or delta r if you will, that's going to be 0. Even though the whole system is moving, and you can pick any point and be like, okay, this point is moving, that's because the system is moving, not because this force of friction is causing that motion. So in this case, the work due to friction, since there is no relative motion, that's going to be 0. 0 work due to the force of friction. Hope this helped. I will see you guys next time.